Let me share my presentation.
শুভ বিজয় স্যার।
Okay, so today we'll discuss about uh, technique for classification. It's a very simple technique that is on linear discrimination, which means that we'll be using a discriminating function which is in the form of linear terms. So let us try to understand what it is. The references are given here. So from the Ethim Alpedine's book, you can go through chapters 10 and 13, and also this book by Duda, Hurt, and Storr, Pattern Classification. So chapter 5 will be useful. So let us try to understand what is meant by a discriminant function. A function, as you understand that it's a function of the corresponding feature vector x, and there would be a set of functions. So the property is that each evaluates certain value. So it provides certain functional values. It's a mapping from the feature space to a real set. So to certain numerical values. Now, uh, there for each class you have a designated function, and for every class you are computing this value. Given a feature vector, you are computing this value. So the function which is returning the maximum value, corresponding class will be assigned to that sample. So that is what is meant by this. That for the ith class, you will find that the ith function, discriminant function, is giving the maximum. So in the linear form, since we will be doing mostly linear discriminant functions, so we will be considering linear form. So in the linear function is in this form, where you can see that there are vector, and every function is characterized by a set of weights, because the functional form is given in this linear combination of these weights. There is, of course, a constant term or a bias term, which is given by this, that also should note that this is a kind of, so this term, which does not make actually this function as linear, we can call it affine, but we can see that a bit modification of the feature vector will make this function as well as a linear function. So we will discuss that. But this is a simple form of the function, and every function set in the set is in this form. So for every class there is a set of weights. Whereas if I try to understand the other kinds of polynomial form of this function, like quadratic function, so in this case, that the terms individual feature vectors, individual feature dimensions, so their combinations would be there in the term. So in the quadratic term, it's a product of those terms. It could be coming, and in the corresponding matrix algebra, it can be very conveniently represented by this form, where you can see that the parameter space, it consists of, say, Wi. So these are the set of parameters. So this is a matrix. If the dimension is D, so it's a D cross D matrix. Similarly, this is in the same way, that this is a vector of dimension D, and which can be represented. So this is that linear part, and then this is that quadratic part where individual fields, pair of fields are coming into the term as a quadratic term, and each one will have a coefficient, and the linear combination of those quadratic terms. So that is expressed in this kind of matrix algebra. So this is these are the set of parameters in this case. That means Wi is a matrix of dimension D cross D, though if I consider the number of terms, it is basically d choose t, d into d plus 1 by 2. That term, that many terms would be coming here, and independent terms would be there. And then this wi, so many parameters. So linear function, it's a linear uniform, and as you understand that you have to store only d fields, d number of fields of white vectors. So, and plus, of course, the bias term. So, order is d, order d storage, and time of computing is also of the same order d. But here in this case, no, since you are also storing the elements of the matrix, so the order is of d square, and that is the same as the time of computations. Now, when we consider only two classes, there we do not require these two separate discriminant functions, because one class, it's one function is sufficient, because no, one of them, so since you are taking the maximum operation, so you assign class to C1 if G1 is greater than G2 or vice versa. So in that case, if I take the difference of these two, then sign of the function, which is also in the linear form, because no, if I consider linear function, so it is also the same linear form. The difference is also in the same linear form. So a single function will be used for classifications, but instead of the max operation, here the sign would be sufficient to denote the classes. So this is the form of the functional form, and as you can see, if Gx is greater than 0, then C1 is assigned, because G1 is in that case greater than G2. Or if Gx is less than 0, then C2 is assigned, because G2 would be in that case greater than G1. So in the other way, geometrically also, you can view this, because it's in the linear form. So it represents a hyperplane in the d-dimensional space. As you can see, that the form of W transpose X plus W naught, that's a hyperplane. So this hyperplane, it divides the space into two hubs, in the feature space into two hubs. One side is positive, the other side is negative. So the positive hub means that if any feature vector belongs to that side, it would be assigned to C1, otherwise the other side would be assigned to C2. So we may consider a vectorial representation in the two-dimensional space like this, that hyperplane becomes a straight line there. So the equation of the straight line you can represent in this form, right? Gx equals 0. That, which means I can say W1 x1 plus W2 x2 plus W0 equals 0, something like that. And then, as you understand that by using the partitions where given any feature vector, which just lies on the straight line, that would be 0, but in one half it would be positive, in the other half it would be negative. And that, in fact, that sign, it depends upon the because you see that it's a dot product of W and X, and of course there is a W naught. I mean, it shows a distance from the origin. W naught gives you the distance. This is a geometric interpretation of the straight line. So if Gx is greater than 0, means that is the side. So along the normal W, along the direction of the W, that side will be the positive, because all the feature vectors, if you take the dot product, it will be the positive. In the other sense, it will be negative. Gx is greater than 0. So this is the distance. If given any particular value, any particular feature, if we compute Gx, the interpretation is that Gx by the normal, by divided by the magnitude of the normal vector. So this is a normal vector. So you get the distance. The sign will determine that in which half it is, and the magnitude will determine the distance. So this is the geometric interpretations. You can extend it to more than two classes. Then you consider the pairwise separation. So only samples of the class lies in the positive. So this is one. Just a different way of interpreting this particular classifier, you may consider this computation is carried out as in a particular node. It's a graphical representation where you can see that the node is representing the node of computations, and in this particular node, which is called, say, perceptron node here. So there are two components. One is that first it will compute the linear combinations of the input components with the weights, and then you can see that how the bias is also taken into consideration, which is set to 1. So this is the input, and this is always set to 1. Okay, so this term, this part is expressing this computation, and then once again, so depending upon this value, right, then there is a function which is finally giving you the level of the class here, classification level, or in the functional form, you can say the output from a function. The simple function could be sign output, because earlier you have computed, as I mentioned, that finally it is a sign which is determining which class level it is. So directly sign is representing a class, which means, say, if the sign is positive, so +1 means, say, +1, and -1 means. So it has two outputs, primarily +1 and -1, and 0 may be a kind of a trivial scenario which you have to, as per your convention, you have to interpret it. So this particular computations, when we model it in this form, we will see later on that artificial neural network, the basic unit in the artificial neural network is this particular node, and it's a network of these nodes finally will be used to compute the input-output responses. So, and that's a very powerful model for either representing classifications, either doing the classifications or doing the regression, that we can see later on. But with respect to this particular discussion, it is the same computations which is represented in a different form. So one of the observations, as we see that here, if the input vector is augmented by an additional dimension and whose value is set to 1, then the operation, this operation can be treated as a linear operation directly. Instead of this affine part, it would be made completely linear if this additional value is, if this part is also added with the input, right, appended with the input in an addition, as an additional dimension. So that is the augmentation. That is the part we call it augmentation, and the feature vector has an additional dimension where the additional dimension value is always 1. Okay, so those who have already gone through geometry and computer visions and other, they know that this kind of a coordinate systems and homogeneous coordinate system, that representation, it is also the same. But from the linear algebra point of view, that this augmentation gives you the advantage of expressing these operation, the linear functional computations, as in this form, so which is completely linear, which means that you are expressing as if the input vector is simply multiplied by the corresponding the weight vectors. It's a scalar product. So that gives you the scalar value set. So this is the advantage if you have this representation, and then you can apply various linear algebraic interpretations and techniques to get to for the analysis. So it is useful for analysis with this kind of representations. So finally, the statement here for a linear discriminant and best classification in this case is that if I give you a set of levels, it's a two-class classification problem that we are discussing. So given a set of levels, say yi and say xi, here xi is the corresponding input feature vector, and yi is the corresponding level. Either it is +1 or -1. It depends upon convention. It could be 1 and 0 also. But in this case, let us consider it is +1 and -1. Then compute optimum W, minimizing the classification error. So So this is a given training set. That means it is not, I will be giving you say n such leveled samples. So which W or which combination of weight combinations or which weight vector will minimize the classification. So that is the problem. Now, of course, the solution is not unique. There could be multiple solutions, and in some situations, this classification error could be zero also. That means exactly we can, given the training samples, we can get a W which will give exactly for all the training samples the correct class levels. Now, geometrically, let us try to understand what are those scenarios where you get exactly the, at least it will be for the training samples. That means a consistent classifier in the language of, if you remember the hypothesis space. So your hypothesis space, as you can see, that the weight vector is defining your hypothesis space here. So interpretations here is that in the feature space, you may consider a hyperplane. And now you can see that since your hyperplane can be simply written as W transpose X equals 0, so which means your hyperplane goes through the origin. Of course, none of your input samples will be an origin because you have augmented it with a additional dimensions and whose value is set to 1. So that is interesting. But no, this is a hyperplane. And in this hyperplane, the space, so there would be two hubs, two sides. It will partition the space, and the one side, the normal will be one side. In the one side, the normal will be directed, so in the same directions. So if you consider a hub, so the side to which the normal is directed, that is one side, and the other side is the normal in the opposite directions. So these are the two sides. And here, in this case, this will be positive. So this is a positive hub because of the directions of W is in this direction, and this is a negative hub. And if X belongs to class 1 and if X prime belongs to class 2, then this is the correct classifications with respect to these two samples. Similarly, our objective is that all class 1s we should choose such W so that it happens that every feature vector of class 1 will lie in this space. Similarly, every feature vector of class 2 will lie in this space, right? So this is our objective. So we would like to get that W, as you say that this is a figurative. And you can see that if I consider the unit vector along W, so that would give the projections, which is which should be positive here, and that itself can be used for determining the distance. If you consider, because it's a unit vector, so W needs to be normalized by the magnitude of the W, then you get the unit vector. So that projection itself will give you the distance. So that is the geometric interpretations. So further, this value D, better is the separability between that sample with respect to the margin of decision, right? So this value is also given some kind of confidence that how good is your classification decision with respect to this. So this is the interpretation, so that you should note here. Right. So this is the other interpretations. So here then comes this particular concept of the training samples. When actually we get a hyperplane which will separate both the classes as per the consistently, right? So when can we get a consistent description of a hyperplane? So there, the concept of linearly separable classes that has come. So that means the training samples for each class it has been given in such a way that they lie. So they there is a possibility that there exists a hyperplane which will classify them, which will separate them out properly under this framework. Then only we say they are linearly separable classes. So this is what. Now, if a solution exists, the classes are called linearly separable under this particular framework. Okay. So, can you tell me that what could be the criteria, say, of linear separability? Linearly separable. How? When do we say these two classes are linearly separable? Is there anyone who can? Okay, so you think about it. That what is the geometric structure by which you can ensure a linear separability given the distributions of feature vectors in the feature space? Think about it. We may also discuss in the subsequent lecture classes. Right. So now let us formally define the error function on which we'll be trying to get a linear discriminant function or a hyperplane which can separate it out. Now, first thing, we'll do certain kind of, there is a certain trick we'll be following to make the problem a bit more simpler, computational problem a bit more simpler. What we'll do that we'll bring all the data points under one side of the hyperplane, which means we'll make a normalization or make a transformation in this way. So suppose if the sample belongs to class 1, there is no change in the sample. But if it belongs to class 2, that means with level -1, then we'll negate the sample. Now, if I negate this sample, which means now this sample, say x prime was here, for example. So if I negate this sample, so this was the sample here, sorry, this was the sample in this direction. So if I negate it, it will come. So the sample will come to the side, in the positive side of the hyperplane itself. So by doing this, actually, what you are just simply finding out whether all these samples, transform samples, are in the positive side of the hyperplane. If it is so, then they are all correct leveling. And if any sample which lies in the negative side, that is the error. So you can very simply define the error in this way, that as we have seen here. So if I consider the product of scalar product of the weight vector and the sample, and if it is an error, then it would be negative. So just take the negative of that, which means make it positive. So if we find all the values which are positive, why misclassified means when this value is negative, then only you are considering. So if you sum all of them, that defines you the error. That defines you the error. So this is the error function, and your objective is to find out that weight vector W, which will be minimizing these error functions given the training data set. So this is your problem statement now. So as you can say that for correct classification, W transpose Y greater than 0. And this error function, we call this error function as perceptron criteria, because as I mentioned that the perceptron node representation is also equivalently expressing the same problem. And this value is always positive, as I mentioned, because of the negation of the negative value. And then you should obtain W, which minimizes this. So very well-known technique of optimization is the gradient descent method in the parameter space. Here the parameter is the weight space. So it's an iterative approach. That means you can start and then move along the opposite to the directions, because you're moving towards minimum, which means if you compute a gradient at that point of the error function, you should move opposite to the gradient, steepest gradient. Move along in the opposite directions of the steepest in the direction of the gradient. And now, how far you should move, that is something you have to decide. But if you move along the directions, you are trying to reach the minimum. So So that is a visual. If you like to make a kind of visual understanding, say in your error function, if you are at this point and this is an error function and this is the parameter space W. So if your gradient direction is this, right, with increasing W, say your error function is increasing, so you should move in the opposite directions, which will be basically, that means your W should be updated in this direction. Then it will take to a lower value, error value, and it will try to reach to the minimum. So suppose it comes in this direction also, there also you have to move along this direction. So in this way, you are trying to reach at a minimum, but that minimum, of course, you can see that it's a local minimum. So unless the function itself is, convex function, which has only one global minimum, if there are many such minimum, that means there are local minimum, then it will be, it will be reaching the local minimum. So that is the kind of limitation of the scheme, but the scheme is very simple, which means you need to compute the gradient value only, and then it should move iteratively. So that's the simple algorithm. You can start with an initial vector, W naught, then compute the gradient vector and move closer to the minimum by updating W. So what should be the step size? That means since you are updating the W, there is a kind of variations. You can see there is a term there is scaling of this vector. This is a scaling term, and this is a step. We call it step size. Now, as you are trying to know, you are near about the optimum point or the local minimum, the step size usually decreases, and if you are further away, the step size usually increases. So, by using the second derivatives or Gaussian of this particular matrix, gradient matrix, you can do that. So please read a book on optimization, and you can get all the details there. So there is a positive scale factor, which is also called learning rate in the jargon of machine learning. So this is the algorithm, a simple, very simple algorithm. So now, if I apply the gradient operations, as you can see that with respect to W, the gradient would be simply y, and since we are moving in the opposite direction, so again negative of negative. So actually the gradient was minus y, and then you apply since you are moving in the opposite directions, it will be positive y. So simply what you are doing in this algorithm is that you are finding out which are the samples misclassified, and you are taking the resultant vector of misclassified samples as the step for updations and a proportional value to that. So that is a simple algorithm. So you should continue till it converges. One thing you note that here you have to process all the training samples, and then you are updating your weights. Now this algorithm can be simplified, as I mentioned. Of course, before going to that, let me also just mention that there could be several other forms of error functions. Like you can have, this is also another error function, where instead of taking as you can see that minus of W transpose Y, you can simply take the square, which will give you the positive value. And then actually the function becomes smoother here. So that is the advantage you have. It's a continuous, very smooth in the boundary, but that is also disadvantage, because in the boundary you may get stuck there. That is because your convergence rate would be very slow there, and you may get stuck. And the value dominated by long Y's, one disadvantage of this particular error function, not only this one, even the previous one, is that if the Y is very large, so naturally, since you are taking resultant, as you understand that particular vector will dominate over the resultant value. So it is better to, because it's the directions, it's the resultant vector you are considering, why don't you normalize it, right? So we can normalize it, and also we can have certain, some margin of, I should say, confidence. Like if it is misclassified only when if the value is less than certain value, B. and then only you are considering. Otherwise, you are not, because of trying to consider that there may be noise and the samples which are lying very close to the margin of the separations, maybe we should ignore them. So that is how we are considering only those samples misclassified with a large margin. So those should be considered, and also you should normalize that separations with respect to the magnitude of the sample value, the sample vector. So this is also another popular error criteria, which is called relaxation criteria, as you can see that this one particularly, where B is defining that margin and it is normalized by the sample. And you can get the corresponding gradient operations. So if I do the gradient computations of the value GRW, right, the relaxation criteria, so this could be computed in this way. You can see that is the gradient, and then you can use it for your computations. So this is the interpretations. If you put B, then you are ensuring at least you are considering only those samples which are misclassified samples, which are at a distance, minimally at a distance between. So this is the distance B by W, B by the norm of the W. So finally, this algorithm, if I just summarize, that you should initialize with W naught, and it is called batch relaxation because you are considering the whole training samples together. So compute first the misclassified samples, and not only that, with margin B, then you should compute gradient, and then you update in this fashion, the same. And you go on doing these things till it converges. But one of the modifications, and which is very effective in computation, is that instead of computing the whole batch, why don't you update at single sample itself? Because that also will take you towards minimum. So and that makes your algorithm is also very simple because now you need not go through the whole training samples. As and when you get a misclassified sample, you simply update that. So this is this algorithm. So for every misclassified sample, immediately you can update the W, and then you can go on doing these things till you get a convergence. So this is called single sample relaxation with margin. So this is how. Any questions till now? Okay, so let me proceed then. Now, this is what we have seen, that actually there could be various solutions of a, given the training samples, there could be various solutions because you can start at local minima. With respect to your starting initial point, you will get one of these hyperplanes, and the error may not be the global minima, but it's a local minima. Now, one of the optimization criteria, you can set an optimization criteria in such a way that you try to get a, you can ensure a particular hyperplane which provides you these maximum separations between these two samples. Particularly if they are linearly separable, you try to get that hyperplane instead of infinitely possible hyperplanes between the space of separations. You may consider only a hyperplane which will try to maximize the separations of these two samples. So we'll be defining these separations of two samples means what is the closest sample with respect to that hyperplane? Closest pair of samples. That means closest from the class 1 perspective and the other class closest. And then how they are separated. Now naturally, you can intuitively you may consider that just visually, if I try to draw something like that, say you have, this is the space of class 1, so this is the distribution of class 2, and suppose you have a sample you have a hyperplane and say this is the separation, this is the closest sample, and this. So if these two are same, which lies in the between, then you get the maximum separations, right? So we are trying to get that kind of hyperplane. So we are trying to define a problem. We are trying to formulate a problem in such a way, an optimization problem, that the answer to that problem would be this hyperplane, which will try to maximize the separation from each of these samples. So let us see this problem formulation. That is very interesting problem formulation. So first thing is that once again, it's a linear discriminant classifications. That's what we would be considering. And in fact, the classifier is called support vector machine, which satisfies this particular criteria, and we'll be discussing about that. Just let me take this call. Okay, so as I was discussing, we are considering a linear. We are discussing about the support vector machine, and we will be considering a linear discriminant classification. Here, we use, of course, this is the principle. It says that never solve a more complex problem as a first step before the actual problem. So the idea here is that, as I was showing you, that while defining this problem, if we can identify the class bounds, then it is sufficient to get a classifier with the samples in the class boundaries only, right? So that is what it tries to say. And so this classification and outlier detections, these are the two important part. So let us go through the problem statement, and those samples which are lying on those boundaries, they are called support vectors. So in the problem statement, we will be considering the two-class problem. Here, you are giving the labeled samples, and then as you can see that it is the sample is in the d-dimensional space, and its label is in +1 and -1. So our objective is to compute that weights such that you can see that we are keeping some margin here also from the hyperplane. That means the value should be +1 and -1, as if they are the class values, and we are trying to keep the same as class value in the numerical sense also. So we are also keeping certain margin. Apart from that, it is not only the separations, at least we are trying to guarantee a margin. So we are writing in this way. So this is the problem that we are trying to get the classes in the form. So we can rewrite in this form like the way we have played that trick on the normalization of the data to bring on the same hyperplane, on the same side of the hyperplane. Here also we are multiplying with the class level. RT is the class level, which is given in the numerical form +1 and -1, and we'll be using that numerical value. So this numerical value is playing in its role in the computation. So you need to note that. So if I multiply, then for all the cases, consistently it should satisfy that it should be greater than equal to +1, right? And it is harder than greater than equal to 0. So this is how the margin is defined. And if it is lying on +1 and -1, which means the hyperplanes are defined in this way. Earlier, we have simply considered a hyperplane passing through the origin, but now, since you are giving a margin of 1 in one side, so in the positive side it is -1, in the negative side it is +1, and the difference naturally is 2 by this. Okay, so this is a separation. Now we would like to maximize this separation. So this is a separation between two classes. This is how the separation of two classes are defined, measure of separation with respect to this problem. So our objective is to maximize the margin, which means we need to minimize the magnitude of the W. So instead of minimizing this, we will be minimizing the square of that and subject to. So this is the constraint optimization problem. As you can see that objective function has been defined in this way that we are going to minimize the square of the norm of W, and we are adding, it's a proportional term divided by 2 because this is a trick, mathematical convenience. If I take the gradient, then this 2 will be cancelled because it's a square term. In the gradient, you get 2 as a coefficient. So if I divide the whole term itself by 2, then that gets cancelled. So there's that kind in the expressions. But it has to satisfy all the constraints. That means all the training sample specifications, which is given in this form. It is for all T. Okay, so this is how the problem is defined. So once again, the optimization problem is a constraint optimization problem, and here the problem is defined in this way that minimize the square of the norm of W divided by 2, subject to that it satisfies all data specifications. For every data sample, its proper classes, which is expressed in this term. Am I audible now?
Yes, sir.
Okay, fine, it's all right. So there was a network issue. Right. So so this is this particular specification. This constraint is imposed from the data specification. As you can see that RT is basically TH sample. This T is superscript. So TH sample, TH data sample, and the TH classes with respect to that data sample, class label. So either +1 or -1. So these are the two values on. So these are all given to you. These are all given to you, but these are the variables. Like you have to find out the parameters. You have to find out these W's in such a way that these are satisfied, and you are minimizing this. So you are minimizing square of this part. In the minimization, this term W naught does not have any effect, but definitely W naught has an effect on this particular for satisfying this constraint. Optimization problem. So to make it unconstrained problem, as you know that we can use this Lagrangian coefficients, use the Lagrangian multipliers, Lagrange multipliers, where the constraints, all those constraints can be linear. They are all in linear form. So you have a quadratic term in the objective functions, and you have a linear constraint. So it's a very ideal case for convex optimization problem. So this is a Lagrange multipliers that you will be using for each constraint. So which means this also now has become a parameter, new parameters. So these are the additional parameters. So we have to find out not only W, we have to find out also alpha T, right? And so that this term gets minimum. Right? Since it is minimum, that's why you are using negative here, and this is a constant coefficient. So this is a simplification. This is simplification from this term, and so you get if I simplify it, you can represent it in this form. Okay? As you can see, this minus and this minus, it becomes positive. So sum of alpha t, it comes from there, from this. And then this particular term is expressed here. Right? So there are three parts of the expression. And we call this particular optimization objective function is primary objective functions because there is a theorem that is for the convex optimizations with respect to a linear constraints that will be applying to convert these optimization problems. So since in this optimization problem, you will be primarily finding out the W. Because for optimization problem, as you know, that you have to make the gradients equal to 0. And since it's minimizations, then of course you have to check the double derivative Hessian matrix, etc. But assuming since it is convex, since you say you know that there is a minimum, so we are not going to make all those checks. But what we are going to do, of course, to solve this problem by solving those by setting partial derivatives equal to 0. But while doing these things, we will get the relationships between alpha and W. And then from there, you solve this problem and you find out W alpha both together. Now you will see that we can convert this problem as an optimization problem only of alphas. That means we can eliminate the task of computing W. We can compute first alpha, all alphas, all these Lagrange multipliers, and then W can be expressed, can be derived from there. So that is the conversions. That is the conversions with respect to this. So let us see how this transformation is done. I mean, once again, it's a summary of that. As I mentioned, it's a convex objective function and you have linear constraints. So the dual problem is that which means that you can maximize with respect to Lagrange multipliers, all positive Lagrange multipliers. Subject to that, gradients with respect to W and W naught should be 0. So this is the constraint once again. The Lagrange multipliers should be positive. That is the constraint you put there. So in the dual problem, you have this. If I perform the gradient, you can see that W is expressed in terms of Lagrange multiplier and the inputs, what has been specified. So a very interesting linear form itself is there with respect to Lagrange multiplier, right? So that you get W. So if I can compute Lagrange multipliers, I would get W by solving this equation, by since this equation for satisfying these equations. Similarly, I can get also W naught from these equations. Of course, W naught gives me these particular relationships, how alphas are related among themselves. So alphas are not independent. All alphas are at least as you can see, there is one equation. So at least one alpha, I mean one less parameter in the alpha space. So if there are n samples, there would be n alphas. So it shows that you can solve for n minus 1 alpha. But the interesting part is that W naught is computed because you know that you are also finding out some of the samples which are at the margin. So if you can find out support vectors, so that means the samples which are lying at the boundary, so then use that linear equations, because at that point linear equation has to be satisfied. That means that should be equal to 0 with respect to that sample value with respect to the support vector, and from there you can get W naught. We'll see those things. So the dual optimization problem is formulated in this way that if I apply these conditions, now you will replace this part, right? That means this W can be replaced by this. Before that, what I will do, I will make some simplifications of W itself. That means, as you can see already, alpha t, RT, and xt, this itself has W. So which means I can represent it also as W transpose W, right? It's a summation term is also there. So which means hello.
काय सुरू आहे? बिझी आहे का?
Please mute your microphone. So in the dual form, you get this. You can simplify it in this way. After putting still we have not replaced anything. We have just we have simplified the expressions or expanded the expression of LP. But now I will be replacing all these W's. First, you can see that this is a W. This part itself is W, right? So that you can observe. No? This one I am just putting here. Similarly, this alpha T RT equals sum is equals 0. So this part will also go. So so W naught will not be also there. So only the alpha T term would be there, and this half W transpose W and this is W transpose W will make it minus half W transpose W. And once again, since you know that W can be replaced by the Lagrange multiplier, so we can simply expand W and we get the expression, dual expression in terms of only Lagrange multipliers. So this is the expressions, and this problem, of course, this optimization problem is a quadratic optimization problem because you see these are the quadratic terms of the parameters. These are all specified. These values are all specified. So you will get a quadratic equation, right? A quadratic objective function, and you have to minimize this. I think it is maximizations. No? Dual problem is objective functions. Yeah, maximize. So you have to maximize that. That is what is the theorem says. Right? You have to, here also it was written. To maximize with respect to alpha t. So, and you'll observe that most of them would be 0. That's the result I'm talking about. So there is a method by which this can be solved. So we are not discussing about the method, rather we'll assume that there is a tool by which you can solve this and you can get the values of alphas after maximizations. And then once values of alphas are known to you, from there you can derive the weight vector W by applying this equation. By applying this equation, you can derive weight vector W, and W naught, of course, is derived indirectly. This equation does not give W naught. So W naught is derived from the support vectors itself, which are lying at the boundaries. So there you apply the equations of the hyperplane. So apply quadratic optimization techniques, and these are the algorithms. It takes order n cube time and order n square space complexity. So most of these, they will be 0. And samples with positive alpha T are support vectors. So using support vectors, you can get W naught. Because all of them will be lying in +1. So you have to satisfy this equation, right? R2WT plus W naught equal to +1. So for numerical stability, you can take average. So whichever samples for which the parameter alpha values are non-zero, you take, and also they are positive. So you take those samples and then you solve this equation for each one. Each one will give you a W naught, and statistically you can take the average of W naught. And this is how how you can get the corresponding hyperplane, which has the maximum separability from the training data set. During testing, of course, you have to only check the sign. You don't bother about +1, -1 there. Just check the sign only. Margin is not enforced, and you can decide the classes. So there, you can consider that. And so let me stop here today. We will continue this discussion again tomorrow. I mean, if the classes are non-separable, then how do you handle under the same framework itself? So let me take your attendance first. If you have any questions, let me know. Announcement I would like to make. One thing is that your third assignment has already been uploaded. In fact, today is the deadline of your second assignment submission. So you can check your third assignment immediately after that or even now. And any query of the assignments you can resolve with the TAs, as they have suggested that please go through them and resolve them as quick as possible. Next week, next Wednesday, I will be busy. So next Wednesday, there will be a doubt clearing session by Jayashree, where you can discuss also some of the things of your assignment. And you will have your final class test. That would be on 18th November. That is the last class of this semester. And it's a Thursday. So once again, it's the same time. It will be, of course, of 1 hour duration. And your syllabus would be also this part only. So that is another thing I would like to inform. Okay. And then again, see you tomorrow. Bye.
Sir,
Yeah.
syllabus would be only after this or overall?
Sorry, I think there were some questions, so I just left. Is there any question? Someone has asked something? Okay, fine. Thanks.
Excuse me,
Yeah.
sir. Actually, the person was asking whether our syllabus is the entire syllabus or
No,
the
no. I
portion
just mentioned that third quiz would be the syllabus after your second quiz.
after a second quiz.
So
Okay,
from today onwards, whatever I'm teaching, that would be there. And I am hoping that I will be able to complete artificial neural network after this,
Okay.
and maybe the ensemble method of classifications.
Got
So
it, sir.
these are the things will be there.
And sir, what is going to be the weightage for each of the three tests?
So I have already told, na?
No, sir. Individually, is the weightage
Individually, it
going
will
to
be
be the
same. If
same?
it is nothing is mentioned, individually it is same.
Okay, okay.
Okay, bye.